Hello again, everyone. Welcome to our discussion of section 3.2, where we will talk more about graphs, this time graphs of polynomials as well. So to begin with, please let me remind you all that the best way to study and learn this subject is first skim through the section 3.2 on your own before you watch this video. Just spend half an hour to 45 minutes reading it, and then watch the video or attend the class and take notes of the things that you think are important or the things you think might be worth questions. And then review your lecture notes and solve all the problems again without looking at my solutions. And finally, of course, complete all homework assignments by the due date. And number 5, continue reviewing the material until the semester ends. Okay, having talked about that reminder that I'd like to give every time, section 3.2 begins with, I should, however, change to the camera here, to dock camera, so you can see it. I just noticed that I was on the computer screen. So during this whole video session, and thank you for your patience as the dock camera starts. And during this whole video session, I'll be going back and forth between the dock camera and the computer screen. When I do that, the signal tends to shift by seeing a blank screen or by seeing a hue of colors before the switch happens. So don't worry about that whenever that happens. So here we are, the dock camera screen is up. Let me zoom in. And so we're good, looks like. And yeah, so I was talking about this sheet earlier, this reminder that I'd like to give all of you. So please make sure that you comply with this list of study strategies for all quantitative subjects: math, economics, finance, all of those subjects, chemistry, physics, all these wonderful subjects. This is the way to study them. So read the book, read the section before it is covered in a video or class, and then and go from there, like I was saying earlier. So with these basic curves, we've been talking about these. For example, this is just a linear straight line. This is a graph of a quadratic equation. This is the graph of the cubic function. And this, notice this graph looks like the quadratic equation, but the bottom of it is flattened. If you notice this, compare this with the bottom of the quadratic function. This one is flattened. It's because the function is y equals x to the 4, not x squared, x to the 4. So when that happens, when you raise x to even powers, 2 and above, it basically does that. If the power is just 2, you get the quadratic graph of the quadratic function, which is that. If you have even powers higher than 2, like 4, 6, and 8, the impact of that is flattening of the bottom of that curve. So if I went to x to the 8th power, you would see that bottom flatten even more. And x to the 10 or 12, that would really flatten the bottom of this. Okay? So that's the impact you see. And of course, the same happens with the cubic function. So with the cubic function, notice how it is as the line graph goes through the origin. And notice had that portion of the graph has flattened out even more in this graph. Why do you think that is? Well, Here you have x to some odd power 5, which is larger than 3. So if you have x raised to odd powers of much larger than 5, it has the same effect as the raising of the quadratic function had to higher even powers, which would flatten this portion of the graph. In this case, with the cubic function, this portion of the graph is flattened more and more. Okay, so if I went to x to the 7th power, that would even flatten even more. So you'd see a great flattening here to here, okay, in comparison with the cubic function. Okay, so we've studied these curves before, in earlier sections, but why is that? Why such great focus on these particular graphs? Well, if you take one reason is that the quadratic graph, the cubic graph, you'll see this a lot occurring in mathematics, in mathematical reasoning and analysis and geometry and such. The other reason is that these graphs seem to be all we need to analyze any kind of graph. So let me, as an example, so if this is x and this is y, so suppose we have a graph that looks like that, right? Something like that. So we can analyze this graph. We can segment it, look at pieces of it, what I mean, and each piece can be one of these forms. Okay, so if I look at different parts of this graph, I can analyze from here to here. That would be almost a straight line from here to here. I can analyze it from here to here, that piece. That's a quadratic function, right? I can analyze it using from, say, here, here, like that, right? That looks like an exponential function. If I extend the analysis from here to here, that's an exponential behavior. So because of that, because of the fact that we can look at a more complicated graph and segment and analyze it using any of these, that itself is another reason why we're focusing more on the properties of these fundamental graphs. They're fundamental to many other graphs in mathematics. Okay, so moving forward with this, I mean, there is a concept called multiplicity of roots, but I will talk about it when we get to the polynomial graphs, but not now. But for now, just keep that in mind. That's why I asked you guys to read the book before you watch the video or come to the class. It's because you already have an idea about these topics in your head, which is fantastic when you attend the initial lecture on any topic. So for now, let's start with this. So using the graphs of the basic functions, that means one of these basic functions, right, like that, basic functions. Using these graphs, transform and sketch the graph of p of x, p standing for polynomial x squared minus 4, calculating the coordinates of the vertex, and the intercept. So we not only have to graph it, we don't only have to show the transformation, but we want to know exactly where the vertex is, and we want to know exactly where the intercepts are. Okay, these are the x and y intercepts. Okay, so the x-intercept or x-intercepts and the y-intercept. That's what they're talking about, where the graph of this function intersects the x and y axis. Okay, so let's do this in order in which they're asking us to do it. So calculating the coordinates of the vertex, well, we learned last time that to calculate the coordinates of the vertex, we have two ways of doing that. Either use the method of completing the square and write this in the standard form, or just use the formula that we had, minus b over 2a, comma, function evaluated at minus b over 2a. But this one is such an easy function, we quickly can see that this is just the original or the basic quadratic function moved 4 units down. So we can easily, we know that the vertex of this, because it's such an easy function, the vertex is at 0, comma, negative 4, right? So this will be here, 0, comma, negative 4 is the vertex, right there. And then the intercepts, let's calculate those. For the x-intercept, the y value is equal to 0, okay? And then we're going to find x values. So in that equation, let's put or substitute 0 for p of x and calculate x values. So 0 equals x squared minus 4. That means x squared equals 4, which means x equals, by the square root property, remember the square root property? It's plus or minus 2, right? Not just 2, plus or minus 2. And therefore, the x-intercepts are 0, comma, positive 2, and 0, comma, this is, so 2, let me correct this with my thicker marker here. So we have 2, comma, 0, and then minus 2, comma, 0. Okay? So those are the x-intercepts. And then the y-intercepts, or y-intercept, is obtained by setting x equals to 0. Okay? So we're going to calculate that function. So y equals 0 squared minus 4, and y equals minus 4. So those were the x-intercepts, and y-intercept would be 0, comma, negative 4, which we already have it, right? That's where the vertex is, like that. Okay, so now we have all the components we need to draw an accurate rough graph of this quadratic function. So let's plot 2, comma, 0 would be this point, minus 2, comma, 0 would be this point. And let's draw a graph of this. So we have, I'll try to draw this as smooth as I can, like that, and like that. Okay, so that's the graph of this function. Okay. This was easy one, but for more complicated graphs, I will switch to the computer to show you a more exact version, because my manual graph may not be as good as it should be. Okay, so sometimes we'll do that. So sketch the graph of this function, calculating the coordinates of the vertex again and the intercepts. So we need to do that. We need to find all of those. Okay, so the vertex, this is in a standard form. So this is easy to find where the vertex is, right? because this is in a standard form. Remember the standard form that we talked about last class, in the last video? This is the standard form of a quadratic function. The vertex coordinates are h comma k. So when you compare this with that, the vertex then is at 4, positive 4, right? Because minus h stayed minus 4, so h must have been 4. If this was x plus 4 squared, then h must have been negative 4. But 4, comma, k, which would be in this case, there's no k, right? So 0. So we know that's the vertex, h comma k, or 4 comma 0. Then the intercepts, so the x-intercept is where y equals 0. That means q of x equals 0. Like that. So we take the square root of both sides. We get 0 equals, so square root of 0 equals square root of x minus 4 squared. And we end up with 0 equals x minus 4, which means x equals 4, or 4 comma 0 is the x-intercept here. For the y-intercept, x should be equal to 0. So in that function, let's substitute for x with, because q of x is just the function y, right, along the y-axis. So 0 minus 4 squared, and this will be equal to minus 4 squared, which is 16. And so so the y-intercept is, let me draw this like that, so 0 comma 16. Okay, so my graph here isn't going to allow me to plot it because it's way up there. So I will estimate where it's going to be, and then I'll go to the computer to show you a more exact version of this. But the y-intercept is going to be at that point, 0 comma 16. Okay, so let's try to plot these. The vertex is at 4 comma 0. And let's see, so 4 comma 0, that would be 4 right there, right there is the vertex. And then that's the x-intercept, that's the only x-intercept we have. Then the y-intercept at 0 comma 16. So the y-intercept would be way up here, right? So I'm going to put an imaginary point here. So this graph should look like something like, and let me say that's 0 comma 16. And then this graph would look something like that, like this, and then come up like that. So it would look something like that. Okay, so let me switch to the computer and show you a more precise graph of this. So we had q of x, or f of x, it makes no difference, x minus 4, like that. So notice that's the vertex, 4 comma 0. And let me switch to the projection mode so you can probably see this better. And projector mode, there it is. So that's probably better visible. So that point is 1, 2, 3, 4, comma 0 right there. So let's snap to it. And there you see the dot appear at the vertex, and I'm going to label it as 4, comma 0. So we said that the y-intercept is going to be at 0, comma 16, right? That's where that is happening. Look at it. It's right there. So let me snap a point to it so you can see it more clearly. 0, comma 16, right there. The green dot, right? Let's label it, and that's 0, comma 16. If I zoom out, you can probably see the whole thing like that, with the x and the y intercepts clearly marked. Okay? So, the next graph, let me switch to the dock camera. So I should probably change this graph so I can plot that on the paper, since it doesn't, the y-axis doesn't go all the way to 0, comma 16. Okay, so the next function, and I almost covered it there, that is, my apologies, this is 3x squared minus 3. So let me make that clear. I'll just write it here. Rx is equal to 3x squared minus 3. Okay, so once again, we want to graph this function by identifying the vertex and the intercepts. So once again, this is we can either use the standard form, or looking at it in this fashion, maybe it is already, we have an answer for that, right? We know that this is just the original quadratic function moved, stretched along the vertical axis using this coefficient 3. So it's stretched vertically, and then it's dropped down 3 units. So the vertex should be at 0, comma, negative 3. Right? It's clear from this. So we don't have to use the formula, and we don't have to use the completing of this square. So the vertex is at is at 0, comma, negative 3. So 0, comma, negative 3 is right there. Okay? That is the vertex. Okay, so the x and y intercepts, let's find those. The x-intercept is when y equals 0. And that is when r of x equals 0, right? 0 equals 3x squared minus 3. Then let's solve this for x. 3x squared equals 3. And then x squared equals 1, right? 3 divided by 3 is 1. And then x equals plus or minus 1 by square root property. We get plus or minus 1, not just 1. So the x-intercepts are 1, comma 0 and negative, comma 0. Those are the x-intercepts. Then the y-intercepts, or y-intercept, usually we have one of these, right? So that happens when x equals 0. So in that equation, let's replace x with 0. So we have y equals 3 times 0 squared minus 3. So that case, y equals minus 3. And so the y-intercept is 0, comma, minus 3, which we already have it, right? We already knew that's the vertex for us. Okay, so let's plot these two x-intercepts, that would be 1, 0. That's one of them is here. The other one is negative 1, 0. That would be here. And this is going to be a stretched or sharp quadratic graph, right? Which we would expect it to be because of this coefficient being larger than 1. In the previous class or videos, one of those videos, we talked about this coefficient that if it's greater than 1, anything greater than 1, there is a vertical stretch of the graph that occurs. If it's between 0 and 1, then you have a flattening of the quadratic graph. So in this case, there's a stretching, and I'll try to show that as best as I can, like that. Okay, so that point here is 1, 0. That's that intercept, and this one is minus 1, 0. Okay, so we can show that by going to our computer. So the graph is y equals, or r of x equals 3x squared. Oops. 3x squared minus 3. Okay. So let me just, because I like to remind you, this 3 stretches the graph. So if I just did x squared minus 3, right? X squared, that's what I like to come to the computer. We can quickly explore different situations to make a point. So suppose I get rid of the coefficient 3 and just say x squared minus 3. See, the purple one, which is the one we were going over on the worksheet, see how much more stretched it is, right? It's narrower, it's stretched towards the y-axis. It's all because of this 3 next to it, or in front of the quadratic term. Okay, and if I added something like y equals 0.1, which is some value less than 1, times x squared minus 3, look at that. It flattens it out, right? We did talk about this. I just like to remind you of what we're talking about here. This coefficient is less than 1. You have this red curve that flattens out more than the versions where you have a coefficient that is higher than 1, which is that 3, which is the purple one. Compare the purple curve with the red one, right? The purple one and the middle one, the black curve is the original, quadratic term has just a positive 1 coefficient, right? It's not less than 1, and it's not larger than 1. So that's what you get, the black curve. And the purple one is when you have a coefficient of the quadratic term that is larger than 1, which is 3 in this case. And then the red one is when you have that coefficient less than 1, and it's 0.1. So look how much flattened or flatter it is than the purple or the black one. Okay, I hope this is making my point clear, this graph. Okay, so let's go back to the dock camera. So the next graph for us is this one. Sketch the graph of this curve, calculating the coordinates of the vertex and the intercepts. So once again, this equation is given to us in the form of a standard quadratic equation. And compare this with compare with s of x equals a times x minus h squared plus k. right? This A, which is 3 in this case, again, it stretches the graph of the quadratic function vertically. So it'll make it sharper and narrower. It'll stretch it up along the y-axis, just like we did with the previous example. That number A does that. Then the h in this case, the vertex then, comparing this with the standard form, then the h should have been 3, positive 3, right? Because minus h is now minus 3. So h must have been 3. If this was x plus 3 squared, then h must have been negative 3. Okay? Just keep that in mind, please. And then what about k? Compare this with that. What about k? What is k now? K is 0. So that is the vertex. The coordinates of the vertex are 3, 0. So let's plot it. 3, 0 is right there. Okay? So let's find the x-intercepts. Or in this case, it's probably going to be that, right? But I want to show it anyway. It's going to be 3, 0. So x-intercept is found by replacing y, or s of x, with 0. So let's do that. So 0 equals 3 times x minus 3 squared. Divide both sides by 3. We get 0 equals x minus 3 squared. Take the square root of both sides. Right? We get 0 equals x minus 3. The 2 and the square root index cancel each other out. So then x equals 3, which means the x-intercept is 3, 0, which we have it, right? That is right here, 3, 0, that point. So we have that. Let's find the y-intercept. I'm going to do that here because I'm running out of or here, starting here. So a dividing line there, and then a y-intercept happens when we have x equals 0, right? So in this equation, substitute the s of x with 0 and solve for x. So 0, oops, let me switch colors here. 0 equals 3 times x minus 3 squared. Divide both sides by, let's see, y-intercept, oops, sorry, let me correct this. So this is y, and this is what I need to substitute 0 for, x. We're solving for y-intercept, so y equals that. Then that is equal to y equals 3 times minus 3 squared. Minus 3 squared is positive 9 times 3 is 27. So y equals 27, which means the y-intercept is at 0, 27. Right? Like that. So once again, my graph does not allow this to for me to plot that. So again, it's okay. Here, I'll just put a hypothetical point way up here, but we'll go to the computer and look at all that on the computer screen. Okay. So for now, for manual drawing, let me do this like that. So this is the graph, and that point, the y, that would be 0, 27. Okay. Okay, so let's go to the computer. So we want to plot s of x equals 3. So that 3 is going to stretch the graph, right? We already know that. X minus 3 square root of, or squared, sorry. Squared. Squared, is that correct? Yes, that's correct. So here's the graph. You can see, you can barely see everything here. I don't want to zoom out anymore because I worry that you might not be able to see it on the screen that well. So this is as far as I'm going to zoom out. So let's now snap the points, the intercepts that we talked about. So the x-intercept is the same thing as the vertex in this case. So let's snap to it. It's at 3, 0, right there, the green dot, right? Let me label it right there, 3, at the bottom of your screen, 3, 0. And then we had the y-intercept, we calculated it at 0, 27, right? So let's snap to it, 0, 27, right there at the top, that purple dot right there, 0, 27 is our y-intercept. Okay, I hope this is making sense as we go through all these graphs. Okay, so let's go back to the dot camera. Here, we have to sketch the graph of this function. Remember when we have even powers of the quadratic function, the bottom of the graph flattens out. Remember that? We talked about that at the beginning of today's lecture. So we're going to have to do that. When I draw the graph, I will reflect that so you can see it. So this graph, we already know that it's going to be have its vertex at the origin right here, but it's going to be really flat at the bottom when you compare it with the x squared minus 7 or the quadratic function. But sorry, the vertex is going to drop 7 points, but it's going to be flat at the bottom. So the vertex here, so the vertex is going to be at 0, negative 7. And the intercepts, we need to calculate that. So this is calculating the coordinates of any intercept. So let's, the x-intercept or intercepts will be when we have the y value equal to 0. So that will be t of x equals to 0 equals x to the 4 minus 7, or x to the 4 equal to 7, or x equals plus or minus fourth root of 7. Maybe I should say that. So plus or minus, let me do it this way. Fourth root of 7, not second root of 7, fourth root of 7, because the left side is x to the 4th, right? So if I calculate that with my calculator, let's do that here. And then we'll go to the computer for that, because the computer does a much better job of drawing these graphs than I can ever do. Okay, so then let's take the fourth root of this, which means raise the 7 to 1/4 power, right? We know that that is equivalent, if you remember the properties of radicals and rational exponents, this is plus or minus 7 to 1 over 4 power. 1 over 4 power. I hope that is clear there on the screen. This is 1 over 4 power. 1 being the power of 7 on the inside, and 4 being the index here, index of the root, the root. So when I calculate it, I'm going to say 7 raised to 1/4 power. It's the same thing as taking the 4th root of that. Okay? And I think my calculator does have a 4th root here, so let's try that. Yeah, so that I see. So maybe if I say 4 and then that, no, I should learn how to use that button on my calculator, but it makes no difference. I can simply say 7 raised to parenthesis 1 divided by 4, and it's the same thing as 4th root of 7. So there is that number, right? Plus or minus that. So that would be, let me round that to plus or minus 1.6. You know, for manually drawing that, I cannot be more precise than that. But we will go to the computer for a more precise graph. So plus or minus 1.6. I'm just going to round this to 1 decimal place, 1.6. So the x-intercepts are minus 1.6 comma 0 and positive 1.6 comma 0. So these are our x-intercepts. Okay. What about y-intercepts? Y-intercept is when x equals 0. So that's an easy one, right? That will be the same thing as the vertex, but I want to show it to you how that is done. So when we find y-intercepts, it's going to be the same thing as the vertex. So y-intercept happens when x equals 0. So in this function, let's substitute for x with 0. So we have y equals 0 to the 4th power minus 7. That is equal to minus 7, which means the y-intercept is at 0 comma negative 7. That's our y-intercept. These are our x-intercepts, and this is our vertex, which is the same thing as the y-intercept. Okay, so let's plot these points. 0 comma minus 7 is that. That's the vertex. Like that. And then these points, negative 1.6 would be somewhere there, right? Somewhere between negative 1 and negative 2. Let me put it right there. And positive 1.6 comma 0 would be somewhere here, 1.6, somewhere between 1 and 2. So now remember, this is x to the 4th, not x to the 2nd power. So when I reach the bottom, I'm going to flat the graph. It's not going to be a pointed graph at the bottom. It's going to have rather a flat bottom. That is when we compare it to the quadratic function. So we're going to come here. We're going to do that. See how I flattened it? And then I'm going to go up like that. Okay, so that's roughly the graph of that function. And of course, this x-intercept is 1.6 comma 0. I don't want to write 4th root of 7. That's why I wrote 1.6. So it would have been more exact if I wrote square root of 7 or 4th root of 7 comma 0 and negative 4th root of 7 on this side. But instead, I'm going to write minus 1.6 comma 0. But of course, when I go to the computer, I will enter a 4th root of 7 and negative 4th root of 7 because the computer can plot those points exactly. And you'll see that it'll be somewhere between negative 1 and negative 2 and between positive 1 and positive 2. Okay, so let's go to the computer and plot this x to the 4th minus 7. Okay, so we have y equals x to the 4th minus 7. And looks like, well, I don't have to zoom out, no. So right there, so we have minus 5 minus, and then let me plot or snap to that vertex, which should be point 0 comma negative 7, right there. And then let's label it, so that is 0 comma negative 7. So the x-intercept, right, it should be between 1 and 2 on this side and negative 1 and negative 2 on that side. Okay, so let's snap to it. I'm going to plot square or negative 4th root of, how do I say, so negative 4th root of 7 to 1 over 4, like that, and then comma 0 right there, right? That's the same thing, but this is, I can be exact here because the computer knows how to plot that. And then, so let's label that. You see, so when the computer labels it, it still does minus 1.6 something comma 0, which is great. So let's do the same thing on the right hand side. So we have minus 7, oh sorry, positive 7, raised to 1/4 power, and then comma 0. So right there. So the blue and green dots show the intercept. So minus 1.6 and positive 1.6 comma 0 there. Okay. All right. Like that. All right. So let's go back to the dot camera. So this next graph, it says that, again, it's an x plus 2 to the 4th power minus 9. So once again, we have the flattening at the bottom of a graph that looks like the graph of a quadratic function, but the bottom is flat because this even power is higher than the second or square. Okay, so because it's in standard form, we can quickly see or write down what the vertex is, right? So the vertex of that is equal to, this is plus 2. So minus 2 must have been the h, and minus 9 is k, right? So that's where the vertex is. Then the x-intercepts, which is when y equals 0. So u of x, let's put 0 for that, and let's solve for x. So we have x plus 2 to the 4th minus 9. So let's move the negative 9 to the other side. Right? And then let's take the 4th root of, not the second root, but the 4th root of both sides. So we're going to have the 4th root of x plus 2 to the 4th power, and we're going to have 4th root of 9, right? 4th root because this power is 4. To cancel it, we have to take the 4th root, not the second root. So on the left, things become very, very easy because the power and everything is gone. This 4th root and this power cancel each other out. We end up with x plus 2. On the other side, because it's the square root, because it's the even root, we have plus or minus 4th root of 9. Fourth root of 9. So then we have x equals, move this negative 2 to the other side, becomes negative 2, minus 2 plus or minus fourth root of 9. So the x-intercepts are minus 2 minus fourth root of 9 comma 0 and minus 2 plus fourth root of 9 comma 0. These are the x-intercepts. And the y-intercept, let's do that here. Let me keep everything on the screen as much as I can. That's as far as I can come down. So now y-intercept, which means x should be equal to 0. And so in this function, let's substitute for x with 0 and calculate y. So y equals 0 plus 2 to the fourth minus 9. Y is 2 to the fourth minus 9. 2 to the fourth is 16. Minus 9 is equal to 7. So the y-intercept, of course, is 0 comma 7. So we know what the vertex is. We know the x-intercepts, which look very complicated. I mean, I don't know how to manually do that, but I will figure it out. And then 0 comma 7. So this is simply fourth root of 9, right? So minus 2 minus fourth root of 9. Let's calculate that. So we have, with my calculator here, we should be able to do that. Okay, so minus 2, right? Minus fourth root of 9. That would be 9 to 1 over fourth power, right? So 9 raised to 1 over 4 power, like that. So minus 3.73, I'm going to round that to minus 3.7, right? So that is minus 3.7 comma 0. That means that one. So that would be minus 2 plus, right, fourth root of 9 plus 9 raised to 1 over fourth power. So we have minus 0.27. Let's say minus 0.3. Right? Let me round that to, well, minus 0.27. Let's write it that way. Minus 0.27 comma 0. So these are the x-intercepts, and I wrote them like that so they are more, we can visualize these or imagine them in our mind better than those numbers. That's why I did that. But with computers, of course, it makes no difference. I'm going to enter in the computer like that because it's going to be exact. Okay? So let's use the y-intercept, the x-intercepts, and the vertex here. The vertex here to draw our graph here. Well, let me do it manually before we go there, right? So vertex is going to be at negative 2, negative 9. So negative 2, negative 9 is way down here, right there. Then we have the x-intercepts. X-intercepts are at negative 3.7. That's a little bit to the right of negative 4, or somewhere between negative 3 and negative 4, right? Right there. And negative 0.27 comma 0. So somewhere here, on the left side of the origin. And because this is to the fourth power, remember this is to the fourth power up here, when I get to the bottom, I'm going to flatten my curve to show that. So this is coming down here, going through that, and I'm going to flatten like that before coming up and going like that. And of course, 0, 7, this one is the y-intercept. Let me not forget that. So 1, 2, 3, 4, 5, 6, 7. That's the y-intercept. So it's going to go through that, like that, and like that. Okay? Like that. So that's roughly the sketch of this graph, and this one is minus 0.27 comma 0 and minus 3.7 comma 0, and this of course is minus 2 comma minus 9, right? Okay, let's go to Desmos.com calculator, desmoscalculator.com, and see our graph in a better shape than what I drew. So y equals x plus 2 to fourth power minus 9. Okay? Like that. Let me see if I can zoom in a little more. No, we can't see the whole thing on the screen if I zoom in more. But I will snap to all these points that we found. Let me first snap to the vertex, which is at negative 2 comma negative 9. Right? Negative 2 comma negative 9, right there at the bottom. And I will label it negative 2 comma negative 9. Let's snap to the next easy point, which is 0 comma 7, right there. That's what we found as the y-intercept. Let's snap now to these two x-intercept. So we have, I'm going to enter it exactly with the square, with the fourth root and everything. So minus 2 minus 9, fourth root of 9, which would be 9 raised to 1 over 4, and comma 0, and did I minus 4, oops, no, that's comma. No wonder it didn't plot it. So there it is. So that's what we have. I rounded it to negative 3.7. There it is. The next one should be negative 0.27. So let's give it the exact point though. Minus 2 plus this time 9 to 1 over 4th power, comma 0. Like that, which is that green right there. So minus 0.268 or minus 0.27. So that's all the points that we had. The y-intercept, the vertex, and the x-intercepts. Okay. So let's continue with the next graph. So, let me switch to the dock camera here. Okay, so we have another another equation to fourth power, which means the graph is going to look like the quadratic equation, but flat at the bottom. And notice this, before the parentheses, a lot is happening, right? This is minus, which means the graph is going to be upside down. It's going to be flipped across the x-axis. And then 2 it's going to stretch the graph towards the vertical axis, or it's going to stretch the graph vertically. Okay, so, but to begin with, compare this. So compare with y equals a times x minus h to the fourth power plus k. Right? Compare that with that. Then the vertex is going to be h comma k, right? H and k, as if you compare this with this, will be the vertex. So the vertex is at, what is the h? Compare this with this and tell me what is the h. The h is -2. If you said -2, watch when you're watching this video, excellent. Because this is always x minus something, right? So if we have x plus something, that means h must have been -2. So minus 2 gives us the +2 that you see here. So h is -2. What about k? Compare this with this. What is k now? K is 0. So that's the vertex. What about the x-intercepts and the y-intercepts? Let's find those. So the x-intercepts happen where y value equals 0. So in this equation, let's substitute for v of x with 0 equals, and let's solve for x. So we have -2 times x plus 2 to the fourth power. Let's divide both sides by -2. We end up with 0 equals x plus 2 to the 4th, right? Dividing both sides by -2, 0 divided by any number is going to be 0 again. And on the right-hand side, -2 is gone because we divided both sides by -2. Okay, so now take the 4th root of, not the 2nd root, 4th root of, because you have the 4th power here. So 4th root of 0 equals 4th root of x plus 2 to the 4th power, right? So on the left we have 0. On the right, things are going to simplify drastically because this 4th in the index and this 4th power are going to cancel each other out. We have x plus 2, and then we have x equals -2. So, so we have, I should remember that when we take the square or the 4th root of both sides, this becomes plus or minus because that's the even root. So plus or minus, and so we have on this side, let's see, okay, so on this side it'll be, I jumped a step too early here, so that'll be parentheses plus or minus, and therefore we're going to have x plus 2, x equals -2. So one of the x-intercepts is going to be what we have already, so which will be -2 comma 0. That's one of the x-intercepts. And then the other one, it's going to be, let me come up here. Then we have the other one, right? Minus. So we have 0 equals -x. Distribute the -1. Let me take this one step at a time. I'm hoping that everybody can keep track this way. So one of these x-intercepts comes from plus of all of this, because when you take the even root of both sides, one side you end up with plus or minus. So that's what we have. The other x-intercept comes from minus all of that. So minus in front. Let's distribute the minus. -x -2. And then let's see what's happening here. Let's see. So we will have one x-intercept then. So x equals minus 2 again, unless I made an error, and minus 2 comma 0. So let's go with that. So both x-intercepts are the same thing. This graph then is intersecting. Yeah, that makes sense. No, that makes sense because the vertex is at negative 2 comma 0. So the vertex is the only x-intercept we have. See, negative 2 comma 0, negative 2 comma 0, negative 2 comma 0. So that's the only place the graph will intersect the x-axis. And then let's find the y-intercept. Y-intercept means that's the location where x value or component is equal to 0. So in this equation, let's substitute for x with 0. We have, and then find for v of x, which is the y component. Minus 2 times 0 plus 2 to the 4th power. Then y equals minus 2 times 2 to the 4th power, like that. So y equals minus 2 to the 4th power is 16, and that'll be y equals minus 32, or the y-intercept then is 0 comma minus 32. So that's our y-intercept. So we have everything we need, right? The vertex, which is the same thing as the x-intercepts, and then we have the y-intercept. So let's graph it. In this case, my axes were not labeled, as you can see. That's nice because then I can increment the way it would fit the graphing area. So for example, to get the negative 32 on the y-axis, I think I'm going to, let's see, I'm going to increment every 10. Would every 10 fit that? So negative 10, negative 20, negative 30? Yes, it would. So I'm going to make these increments 10. So that's negative 10, that's negative 20, that's negative 30, and this is negative 40. So negative 32 would be somewhere here. Somewhere here, negative 32, right there. That's the y-intercept. So 0 comma negative 32, right? And then the x-intercepts, which are the same thing as the vertex, negative 2 comma 0. So that would be, if this is negative 10 on this side and positive 10 on that side, so negative 2 comma 0 would be, if this is negative 5, so this would be here somewhere. Let me see. Yeah, so this is a pretty narrow that. Okay, so this is the vertex at negative 2 comma 0, which is also the x-intercept. So one thing I didn't mention, but I forgot, but check this out. This is minus. The coefficient of this whole thing is minus. So what does that mean? The graph is flipped across the x-axis. It's upside down, right? So this is that a minimum point or maximum point then? If it's flipped, if the graph is flipped, this is the maximum point, right? Maximum point, the vertex is. Okay, so let me try to draw this as best as I can, and then we'll go to the computer, which does a much better job than I can. So this is the vertex. I'm going to draw it like that, but there should be a flattening here because this is to the 4th power, the original function, and then we'll come down here and go through the y-intercept like that. Okay, this is as best as I can draw this manually, like that. Okay, so let's go to the computer for a more pleasing graph. So I'll just clean this up first. All right. And then we have this graph, which is v of x or y is equal to minus 2 times x plus 2 to the 4th power, right? So this is what we have. Oh, I need to zoom out, otherwise you won't be able to see the y-intercept. Okay, so that's that. So let's snap to all the points that we found, such as the vertex. Okay, so the vertex, the vertex and also the x-intercepts were at -2, 0, right there. Let's label it. That's that. Then the y-intercept was at 0, -32. Right there with the red dot, right? So let's label it 0, -32. Okay, so you can see the flattening. I mean, it's very, very subtle, so it's hard to see, but there's a flattening at top of the curve. That's because of the 4th power of this. Let me open this up so you can see it. That's because of the 4th power of this function, okay, or this polynomial. Okay, so we're going to go back to the dock camera again. Oh, so we now reach the cubic functions, right? Remember these? So the cubic function then is, in this case, it's just the original cubic function is where we have just the x cubed, like that. If I cover it, that's the cubic function. But this time it's -8, so the vertex, or not the vertex, but the inflection point in this case, the cubic function has this inflection point and or transition from concave down to concave up, and that's something you look at in calculus 1. I shouldn't maybe use these terms because we haven't talked about concavity at all here, because that's a subject we talk about in calculus 1. So let's graph it manually and with the computer, and you'll see. So for now, this graph, the intercept is going to be along the y-axis. So this will be the y-intercept. It's easier to calculate immediately, and that's when x equals 0. So if you substitute for x with 0, what do you end up with? You end up with y equals 0 cubed minus 8, or y equals -8, which means the y-intercept is at 0, -8. That's the y-intercept. How about the x-intercepts? So x-intercepts, let's see how many we have. X-intercepts occur when the y value is equal to 0. So in this equation, let's substitute for the wx with 0 and solve for x. So x cubed minus 8. And then we have x cubed equals +8. Now we take the third root of both sides, right, to cancel this power. Because we're taking the odd root of both sides, odd meaning because the index of the radical expression will be 3, so it's odd, then we're not going to end up with plus or minus. The plus or minus root of something which is the extension of the x square root property, happens only if we have to take an even root of both sides. So in this case, let's just take the third root of both sides. So third root of, so we take the root that is equal to that power. Otherwise, we won't be able to cancel that power. That's the reason. So, and then third root of 8, right? Because it's an odd root, we're not going to end up with a plus or minus. It's just going to be whatever the sign this had. If this was third root of negative 8, we would end up with something some negative value. If this is a positive like it is now, we end up with a positive value. Okay, so on the left, things are becoming very easy. X equals, on this side, third root of 8. So let's see what is that value. Let's look at it on my calculator here. All right, so we have third root of 8, which we can calculate as 8 raised to 1/3 power. So it's 2. So it's 2, right? So x, or in other words, we can look at it this way. Third root of 8 is 2 cubed. And because the index and the power on the inside are equal, so x equals 2, which means the x-intercept is at 2, 0. Okay. All right, so these are not too bad, because we can plot them on the axis that I have. In other words, they don't go off this axis like the previous examples. So 0, negative 8, that would be here. And then 2, 0 would be here. So the cubic function, we're familiar with the general look, right? So it would come like this. And then it would go like that and come down like that. So that's the general look. But my graph, of course, is not that great. So let's go to the computer to see an accurate graph of this function, x cubed minus 8. So we have, in this case, we had wx, so I'm going to use that. It makes no difference. You can use wx or y. And then x cubed minus 8, right? Like that. So let's snap to the x and y intercepts we found. We found that the y-intercept was 0, negative 8, 0, negative 8, right there, where you have the y-intercept. And then the x-intercept we found as 2, 0. So let's snap to that. 2, 0, right there. And let's label that. So that's the x-intercept and the y-intercept we found. Okay, I guess we can zoom in on that one to see it better, like that. Can we zoom in a little more? Yeah, we can. That's great. Okay, like that. Okay, so let's go back to the dock camera. So here, an interesting thing happens because we have minus x cubed plus 2. So this minus x cubed will flip. It will flip the cubic function across the y-axis this time. Across the y-axis, and then it will move up that inflection point 2 units up. So the vertex, or not the vertex, but let's just call them intercepts. So the x and y intercepts. So just like before, y-intercept, and this would be x equals 0, right? That's where the y-intercept will occur, or occurs when x equals 0. So in this function, we're going to substitute for x with 0, minus 0 cubed plus 2, y equals 2. So 0 comma 2 is the y-intercept. How about the x-intercepts? So let's find those. Like that. So the x-intercepts are wherever the y value is equal to 0. So let's substitute for a of x or y with 0. Then minus x cubed plus 2. We're going to solve for x here. So x cubed equals 2. We have to take the third root of both sides, right? So third root of x cubed and third root of 2. Okay? So the third root, because we need to get rid of this third power. So because of this is an odd root, we do not get plus or minus. Again, if you're taking the odd root of both sides, let's say third root, seventh root, ninth root, 11th root, any of those odd roots would mean that this side, if it's negative, it will stay negative. If it's positive, it will stay positive. Okay? So on the left, we have x. On the right, we have third root of 2. Let's calculate this number for ourselves. So using my calculator, I can easily calculate that by saying 2 raised to 1/3 power. Like that. Oh, sorry. No, I made an error here. 2 raised that 1 divided by 3. So we have 1.259. Let's round that to 1.26. Okay? So x is equal to roughly, approximately equals to 1.26, which means the x-intercept is at 1.26 comma 0. So we have everything we need. Let's plot these 2 points. 0 comma 2 would be here. 1.26 comma 0 would be somewhere between 1 and 2, right there. Right? And because of this minus, the cubic function is going to be flipped this way. So instead of going this way, instead of having this general form, it's going to go like that. Okay, because of this minus. So we will have, I'll try to do this as best as I can. Like that. It'll be like that and like that. Like that. Okay. So let's go to the computer for a better, more accurate picture. So we have a of x equaling minus x cubed plus 2. Right? So let me bring this down. So there, you have this minus in front of the x cubed term that flips this graph of the cubic function across the y-axis like that. So it's going like that. instead of an increasing function, it becomes a decreasing function. Right? So let me for a second, I'm going to bring this up and I'm going to delete it because I don't want to make this screen too crowded. But if we plot the general cubic function like that, okay, notice that the general cubic function is an increasing function. It's an increasing function from left to right, right? We're increasing. We're moving up from left to right. We read graphs from left to right. So it's increasing from left to right like that. But I'm going to delete this. But this minus x cubed plus 2 is a decreasing function. You see that? From left to right, we're declining. We're moving down. Okay, that's because of that minus in front. Okay, so let's snap to the x and y intercepts that we found. We found that the y-intercept was at 0, 2, right there, right? The blue dot right here. That's the y-intercept. Let's also snap to the x-intercept, which was parenthesis third root of 2. So third root of 2 would be 2 to 1/3 power. So 2 to 1/3 power, comma 0. Oops. No. Comma 0, which is 1.26. So let me label it right there, 1.26 comma 0, what we calculated in with the calculator. Can I zoom in a little more? Maybe, yeah, that's even better. So you can see it a little bit up close, or more up close than before, right there. Okay, with the x and y intercepts clearly shown. So let's switch back to the dock camera. I know every time I switch back and forth between the dock camera and the computer, the screen blanks out, and I apologize for that, but I feel that in this lesson, in this video, we have to do that. If I didn't switch to the computer and you just saw my manual drawings, which are not that great, it would be, the quality of the lesson would be less than if we switch. But of course, as I switch from the dock camera to that, you see this glitch in the screen. But that's a minor disadvantage. Okay. So this one says sketch the graph of this function minus all of this cubed. So this is, it's going to look like the cubic function. It has a general form with the minus in front again, which indicates a flipping across the y-axis. So let's calculate it. Let's find where it is, the intercepts and everything. So the x-intercept, that's when the y value is equal to 0. Let's find that. So we have the 0 equals minus x plus 2 cubed, right? Now let's take the cube root of both sides. Or, I mean, you can divide both sides by -1. It makes no difference. But a third root of 0 equals third root of minus x plus 2 cubed, right? On the left we have 0. On the right we have minus x plus 2. And this is 0 equals minus x minus 2. and x equals minus 2, or the y or the x-intercept is negative 2 comma 0. Okay, so that's the x-intercept. And then the y-intercept, let me put that here. Let me try to fit all that here. Y-intercept, that's when x equals 0. So in here we're going to replace for x with 0. So y equals minus 0 plus 2 cubed. And we have y equals minus 2 cubed. Y equals minus 8. So the y-intercept is 0 comma minus 8. Okay, let's plot these points. Negative 2 comma 0 is here, and 0 comma negative 8 is here. Okay, so and that negative means that the direction is going to be like that. The graph is going to go like this. Let me try my best to draw this as best as I can. So we'll come down here, we'll go like this, through this, and then we'll go through that y-intercept right there. Okay. So that is negative 2 comma 0, and that point should be 0 comma negative 8. Okay. So let's go to the computer again to plot this and get a more accurate graph. We start with b of x equals minus x plus 2 cubed. And let me zoom out like that. Okay, can we zoom in a little bit and see the intercepts? Yeah, we can still see the intercepts. So let's snap to each intercept. I'm going to snap to the x-intercept first. So that'll be at minus 2 comma 0. Let's label it. That's that point. And the y-intercept is at 0 comma negative 8, like that. And let's label that. And that's at the bottom of your screen over there. Okay, so that's what we have here. Much better drawing, isn't it, than what I did. Especially if we zoom out, this is a much better drawing. Okay, so we're going to switch back to the dock camera. Here we have it says sketch the graph of 1/2. Notice this coefficient is now less than 1. So our graph, our cubic graph, is going to flatten. It's going to flatten at this point. So you see how much sharper this is? With a coefficient that is less than 1, when the graph gets to that point, it's going to flatten out, okay, because this coefficient in front is less than 1. Okay, so let's calculate the x and y intercepts. For the x-intercept, that's when the y value is equal to 0. So we have 0 equals 1/2 times x minus 1 cubed plus 2. So let's move this 2 to the other side, and I'm going to keep this coefficient positive. Well, let's multiply both sides by 2 first of all, because I want us to get rid of this fraction. Multiply both sides by 2. So on this side we have 0, of course. On that side we have 2 times 1/2 times x minus, well, I'm just distributing this like that, plus 2 times, right? 2 times 2, right? I distributed this to that term and to that term. Now, this 2 times all of that, this 2 and this 2 cancel each other out, like that, like that. We get x minus 1 cubed. This 2 times that 2 is 4. Okay? Then let's move this to the other side because we're solving for x, which means we're trying, everything we do is with the objective of isolating x, as long as we're solving for that variable. So I'm going to move this to this side, so x, and I'm going to keep this positive, this coefficient positive. So x minus 1 cubed equals minus 4. Let's take the third root of both sides. So third root of x minus 1 cubed equals third root of minus 4. This 3 is equal to that 3. They cancel each other out. And nice and easy on the left side, right? X minus 1. On that side, we have third root of minus 4 to third root of minus 4, which is the same thing as minus 4 to 1/3 power. These two are equivalent forms, right? We learned that when we reviewed in chapter 1 the properties of radical expressions. Remember that? All of this makes use of the tools we learned in chapter 1. Okay, so what is this quantity? This quantity would then be x equals, let me move this up a little bit, x equals minus 1, move to that side, 1 plus minus 4 to 1/3 power. So let's calculate this number, right? Because right now it's hard to imagine what this number is. So x equals 1 plus, I'm going to calculate that. Let's do it on my calculator here. Minus 4 to 1/3 power. Right? Let me put this so you can see the whole thing. So I'm going to calculate this piece and put it here. So minus 4 raised to 1/3 power, 1 divided by 3. So it's minus 1.587. Of course, I'm going to round this to minus 1.6. Okay? So 1 plus minus 1.6. And then so x would be equal to minus 0.6. So the x-intercept is minus 0.6 comma 0. And of course, please keep that in mind that I rounded things there. So this might be a little off. I'm sure it's going to be a little bit off, but not much with the number that we'll see on the computer in a minute. Okay, but that's the x-intercept. Let's find the y-intercept. I will try to put that here if I can. I'll do my best to squeeze all of that calculation here like that, so you can see, you can still see the function barely at the top of the screen there. So the y-intercept is when x equals 0, right? So in this function, let's substitute for x with 0 and solve for y. So y equals 1/2 times 0 minus 1 cubed plus 2. I'm going to skip a few steps because I want to fit my solution here. So this would be minus 1 cubed, which is minus 1, plus 2. I have to observe the order of operation. So minus 1 cubed is minus 1. Again, minus 1 times 1/2 is minus 1/2. Minus 1/2 plus 2 is positive 1.5. Positive 1.5, that would be y equals positive 1.5, or 0 comma 1.5 is the x or y intercept. Okay, sorry, I had to skip some steps in order to be able to fit this, the rest of the solution right there in the space that I had left. So here we have the x-intercept and the y-intercept. Let's plot them. Minus 0.6 comma 0 would be somewhere here, right? Minus 0.6 comma 0, and 0 comma 1.5 would be somewhere here. So that one is 0 comma 1.5, and that one is minus 0.6 comma 0. So let me draw my graph as best as I can. Let's see, did I account for that? Yes, I did. Okay, so it'll be like this, coming through here and then going through that. Okay, so that's just a manual construction of that. Let's go back to the computer. So we're graphing c of x equals 1/2 or 0.5. If you want to enter it as 0.5 on the computer is fine. X minus 1 cubed plus 2. Right? Like that. Let me zoom in a little bit. Like that. That's better. And then, so that's the function we've plotted. And then let's snap to the x and y intercepts that we found. So this will be, so let's find negative or, let me see. So I'm going to enter it as an exact value. So let's see where it comes. I'm talking about the x-intercept, which I rounded to minus 0.6. So I'm going to keep that exact by saying 1 plus negative 4 raised to 1/3 power, all of that, comma 0 right there. So let's label it. Oh, so it's this one. It didn't round, the computer didn't round as much as I did, so it kept minus 0.587, whereas I rounded and I got minus 0.6. Okay, and then let's snap to the y-intercept there, which was at 0 comma 1.5, right? 0 comma 1.5. Oops, yeah, that should be comma. 0 comma 1.5. Oops. No, what happened here? No, not 1/5. I entered 1/5. So 0 comma 1.5. Okay, now it looks good. It looks correct. So that's the y-intercept. And something else is happening here. See that where the we have a shift from this form from a concave down to concave up. Again, I hesitate to use these words because these are terminologies you'll see in Calculus 1. We don't use that in Pre-Calculus 1, but concave down is that shape, and then there is an inflection point here where the graph changes from concave down to concave up like that. So that point is 1, 2. Well, let's snap to it. So and I didn't talk about it when I was going through this manually right there. So that point is 1, 2. How do we get this point? You can easily know what the coordinates of that inflection point is by looking at the original function. Remember, the general form of all these functions, going back to when we talked about transformation of functions, remember all that? Going back to that, the general form is always x minus h, then to some power or absolute value or something, plus k, right? So this x minus h, in this case we have x minus 1, which means h must have been 1, which is shifting the original graph of the cubic function 1 unit to the right, right? We learned that when we talked about transformation of functions. So h is positive 1 and k is positive 2. So 1, 2 reflects that h, 2. Okay? All right. So let's switch back to the dock camera. Okay, so here it says, sketch the graph of each of the following polynomials. We got to the polynomials. Because of that, I need to say a few words before we can move forward with the rest of this lecture. So, with polynomials, so let me title this as graphs of polynomials. Okay, this is very important. Suppose we have the following polynomial in factored form. So it would be polynomial x minus 2 squared times x plus 1 cubed times x plus 5. Okay? That's a polynomial in factored form. Now, notice the powers. Now, well, let's first find the zeros of the so let us find the zeros of this polynomial. Which is all x values for which p of x equals 0. So when we talk about the zeros of a polynomial, we're talking about all x values that would make this expression or this polynomial equal to 0. Okay, we want to find all the zeros. So that means, So that's easy to do because the polynomial is in factored form, right? So then we say x minus 2 equals 0. Therefore, x equals 2 is a 0 of this polynomial. Then, from the other factor, x plus 1 equals 0. Then x equals negative 1, right? I'm sure you're following this because if x here is negative 1, this term is going to be 0. Multiplying by all these terms, it will make everything equal to 0. If this x is equal to 2, then that factor is equal to 0, and it will multiply itself by all of this, and it will make the whole expression, or p of x, equal to 0. Now, the third factor, x plus 5 equals to 0, then the x is equal to minus 5. That means if this x is equal to minus 5, then that term will be 0, but because that term is a factor of all of this, it will multiply everything by 0, and therefore it will make p of x equal to 0. So these are the zeros of this polynomial, x values that will make this polynomial equal to 0. Now, associated with each of these zeros of the polynomial, there is something called the multiplicity of the zero. So, for this one, the multiplicity equals 2. The multiplicity is always equal to the power of the factor from which the 0 came from. Again, the multiplicity is always equal to the power of the factor from which the 0 came from. So the power of that factor is 2, so the multiplicity is 2. This one, this 0, has multiplicity 3. Right? Because that's the power of the factor from which the 0 of the polynomial came from. Right? It has a power 3. And what about minus 5? What is the multiplicity of minus 5? Can you tell? The multiplicity is equal to 1. Okay? Because that's the power of the factor from which the 0 of the polynomial came from. Okay, so this is how we find the zeros, and that's the multiplicity of each 0. Now, so at these points, so if these are the zeros of the polynomial, if these are the zeros of the polynomial, these are the points x values at which the graph of the polynomial, here's the important part. What happens at each of these x values? What happens to the graph of the polynomial at each of these zeros of the polynomial is very important. I hope I have your full attention as you're watching this video. So, these are x values at which the graph of the polynomial, case 1, there are two cases, two possible cases. Case 1, the graph of the polynomial crosses the x-axis if it has odd multiplicity. So if the multiplicity is odd, which happens for which one of these? For -1 and -5, the multiplicity is 3 and 1. So those are odd multiplicities. So the graph of the polynomial will cross the x-axis at those x values. It'll go right through the x-axis. That's if the multiplicity is odd. Case 2, the graph of the polynomial touch the x-axis but not cross it, but does not cross it, or but not cross it if the zero, if it has even multiplicity. Okay, so which is only this 0, x equals 2, has multiplicity 2, which is even, right? If the multiplicity is even, the graph of the polynomial will touch the x-axis, but it will not cross it, if it has even multiplicity, which is at that point, x equals 2. So if it's not crossing it, what will it do? Well, if it cannot cross it, then the line will bounce back to the same side. Okay? If the multiplicity is even, the line of the graph, the graph of the polynomial does not cross the x-axis. Instead, it will bounce back to the same side. If it's along the, if that side, if the line is coming from the positive y value side, it'll bounce to the same side, positive values. If it's coming from below, if it's coming from where the y values are negative, then the line will bounce back to the same side where y values are negative. Okay? So I wanted to cover that. This topic is very, very important, and I had to cover it here. So this sheet that you see me describe all this information, I will post all of this on the lecture notes that I post on Canvas. It'll be there. Okay? And if you have any, if you feel confused about this, please rewind the video, go back to where I started talking about graphs of the polynomials, and rewatch this section, because this is very important before we start talking about graphs of polynomials. Okay, so now, having talked about that, and of course we're going to talk about this example, but I have summarized what I said on that sheet. I have summarized it here in this box, which you see. Oops. Okay, now it's focused again. For a minute, the screen went out of focus. Okay, so here I'm saying in a polynomial with roots of odd multiplicity, roots is the same thing as zeros of the polynomial. Okay, I can write it here. So roots are equivalent to zeros of a polynomial. So in a polynomial with roots or zeros of odd multiplicity, odd-powered binomials, the graph will cross the x-axis, which is what I said. For roots of even multiplicity, the graph does not cross the x-axis. So there is the summary of what I said right next to the graph, because it's so important to keep that in mind as we graph the polynomials. If you remember this, graphing polynomials is a piece of cake. But if you forget it, they can be pretty confusing. So please make sure you spend some time on that, just making sure that you know exactly what that talks about. Okay, so here we want to graph this polynomial, calculating any coordinates of the intercepts. So first of all, let's find the x-intercepts i.e. the zeros of the polynomial. Okay, so we want to find that first. So let's set each one of these, x minus 1 equals to 0, x equals 1. What is the multiplicity of this? The power is 1, right? So it's got multiplicity is equal to 1, which is an odd number. So the graph of the polynomial will hit that point, multiplicity 1, at 1 comma 0. X equals 1 comma 0. These are the x-intercepts or the zeros of the polynomial. So it has a multiplicity 1, which means the graph of the polynomial will hit the x-axis at that point and cross it to the other side. If the line is coming from below, it'll go to the above, it'll cross onto above the x-axis. If it's coming from above the x-axis, it'll cross to the area below the x-axis. That's what it's saying, because the multiplicity is odd. So x plus 1 equals to 0. That's the second factor. Then the zero of the root of the zero of the polynomial, or the root of the polynomial, or the x-intercept, it's going to be it has once again multiplicity 1. The power of all these three factors is 1. So multiplicity is equal to 1 again at negative 1 comma 0. The final factor, x minus 5 equals to 0. We have x equals 5. That one also has multiplicity 1, right? The power of x minus 5 factor is 1. So multiplicity equal to equal to 1 at 5 comma 0. Okay. All right. So let's find the y-intercept or y-intercept. That's when x equals 0, right? We can easily find that. Let's just replace x with 0 in all these factors. So we have y equals 0 minus 1 times 0 plus 1 times 0 minus 5. Y equals, that's minus 1 times minus 5. Y equals minus 1 times all of that, positive 5. And we have 0 comma 5 as the y-intercept. That's the y-intercept. All of these are the zeros of the polynomial or the x-intercepts. Okay, so as we plot the graph of this polynomial, please keep in mind what we talked about, odd multiplicity and even multiplicity of these zeros, because for all of these the multiplicity is odd. So at all these points the graph of the polynomial will cross the x-axis onto the other side. Okay, so we're going to plot all these points first. Can I put this so you can see them? Maybe, let me try. Maybe I can. Well, this one I can't, right? Well, no, actually I can't. So I think, okay, I'm going to put the page like that so you can see everything. So 1, 0 would be here. -1, 0 would be here. 5, 0 would be here. And 0, 5 would be here. Okay? So these are all the points where the graph of this polynomial has to cross. Now, drawing the graph from this side, we know that the multiplicity of this 0 is odd. So, and we have an y-intercept here. So, because the multiplicity at this root or 0 is odd, that means the line is coming from below and crossing the x-axis to the other side and hitting the y-axis there. So let me draw it like that. So we have that on this side. The line is coming, going right through that point, which is -1, 0, going through this point, which is 0, 5, coming back down. Remember, the multiplicity is odd at both of these points. So it's going to go right through it. It's going to cross through it because the multiplicity is odd at that 1, 0. And it's going to, at some point, it's going to curve back up. Some point. So at some point, it's going to bounce back, come around, and go right through this. At this point, we don't worry about where is that lowest point. Our main concern is where are the x and y intercepts and what are the multiplicities, so that we know when and where the polynomial graph will bounce back or go through the 0 of that polynomial or the x-intercept. Those are the important concepts at this point. Okay, now this, I will go back to the computer to graph this, but what I'm saying is that where this curves back up, it doesn't matter in this case. So what matters are where are the intercepts, and for the roots or the zeros of the polynomial, which are these 3 points, what are the multiplicities? So we know whether the line crosses the x-axis or whether it'll touch the x-axis and bounce back to the same side. So this is the rough sketch of this polynomial. Let's go to the, oops, let me move this up. I was talking about where this curves back up. Sorry about that. It was off the screen. So I was saying that because it was off the screen, let me repeat it very quickly. This curvature, I've estimated it, but I don't know exactly where that curvature happens. But in this lesson, it doesn't matter. Our focus is on where the intercepts are and what happens at each 0 at these 3 points. Does the line cross the x-axis or does it bounce back to the same side? For all of these 3 points, the line will go through or cross the x-axis because the multiplicity of each one of these zeros is an odd number, which was 1. Okay, so let's go back to the computer and plot this nice polynomial on the computer. Okay, so this was p of x equals x minus 1 times x plus 1 times x minus 5. So let me zoom out so you can see. Right there. So this curvature point, mine is way off, but that's just the general form of this graph of the polynomial is what we are mainly concerned about. Okay, so let's snap to each of the intercepts. The 0, 5 right there, and let's label it. The 1, 0, oops, right there. The negative 1, 0, which is right there. And finally, the last 0 of the polynomial, or x-intercept, which was 5, 0. Okay? There are all the intercepts. I don't know if I can zoom in. Yeah. So you can see it a little bit better right there. This bottom, what you see is called the inflection point. And in this case, where we switch from decreasing to increasing, right? It's going from left to right. It's decreasing, and then it's increasing. And that, in Calculus 1, we know exactly where that happens. That switching happens. Okay? For the exact location of this, if you're going to be taking Calculus 1, you'll see that in detail. But it's not the subject of this course. Okay, so I'm going to switch back to the dot camera. Sorry. I forgot to, sorry about that. My apologies. I forgot to switch to the computer screen as I was talking about all of that. Again, my apologies. So I'm a little bit mindful of the time of this video, which is about to run out. So I'm trying to finish this section before we run out of time. But with apologies again, let me go over this. So these are the intercepts, the y and the 3 zeros of the polynomial. So that's -1, 0, 1, 0, 5, 0. And then I was talking about this one when I was referring to Calculus 1. Where this happens, at the bottom of your screen, where that curvature happens when we switch from decreasing line, going from left to right, to increasing and going up, that is, we know exactly where that point is at the bottom, the coordinates of that point, inflection point, in Calculus 1. But I was saying earlier that topic is not the subject of this course. Okay, that's all. That's why we kind of leave it. When I drew it manually, it was, I estimated it. But in Calculus 1, we have techniques that can help us manually draw that information very precisely. Okay, all right, so that's that. Okay, now let's switch back to the dot camera. So here, this should go more smoothly because now we know how the procedure works. So the first factor, let's find the x-intercepts. i.e., these are the zeros of the polynomial. Okay, where x-intercepts are, by the way, where y is equal to 0, right? So let's replace p of x with 0. So we have x minus 1 squared times x minus 4. That means whenever x minus 1 is equal to 0, this whole thing is 0. So x equals 1. That's one of the zeros, and the multiplicity is even, right? Because it's 2. Power of that factor is 2. So multiplicity is equal to 2, and that is 1, 0, on the x-axis. And this next factor is x minus 4 equals 0, right? So when that factor is equal to 0, it'll multiply everything by 0, so the whole it'll be the whole polynomial will equal to 0 at that point. So x equals to 4. That 0 has multiplicity equal to the power of that factor, right, which is 1. And this would be the x-intercept 4, 0. And then let's find the y-intercept. This is where x equals to 0, right? So then x, so here we have y equals 0 minus 1 squared, 0 minus 4, y equals minus 1 squared times minus 4. So y equals minus 1 squared is positive 1 times minus 4. And so we have y equals minus 4, which is 0 comma negative 4. So this y-intercept does not have any multiplicity. Multiplicity is only associated with the zeros of a polynomial, not with the y-intercept. Okay, so we have the x-intercepts here. We know the multiplicity of each. So let's plot this polynomial. Let me see how far I can move this up while keeping everything on the screen like that. So plotting 1 comma 0 would be here. 4 comma 0 would be here. 0 comma negative 4 would be here. Okay. So that's 0 comma negative 4. This would be 1 comma 0 and 4 comma 0. Okay. So now the line at this point 1 comma 0 has multiplicity even. The important thing about multiplicity is either whether it's odd or even. It's even, so we know the graph of the polynomial, when it hits that point, it does not cross the x-axis. It'll bounce back to the same side. So if we have a y-intercept on this side and we have an x-intercept here, the line must be coming from here. So the line must be doing this. Must be doing like that. Notice, because of the even multiplicity, I'm going to hit this. I'm not going to cross it. The line is going to touch the x-axis and bounce back to the same side. Then it's going to bounce back, come somewhere at this point, which I said it's not the topic of this course, but we will look at that in calculus. It's at some point here, it'll curve back up again because it has to go through this point. This is 4 comma 0. It has multiplicity 1, which is an odd number. So the graph is going to cross the x-axis at that point and go like that. Here, we don't know what happens, right? It could curve back up like this. Again, that's the subject of calculus 1. Or it's going to go through all the way like that. So I'm going to basically do that to it. Okay, because we don't know if it's going to continue this way or curve like that. We don't know. But that's basically the general graph. That's the general graph of this polynomial according to the techniques we've learned in this course. Okay, for a more precise graph, we will do that, or we will take that up in calculus 1. So let me switch to the computer so we can see an exact graph of this. Okay, so we are going to, let me delete all of this. So in this case, the polynomial was x minus 1 squared times x minus 4. Okay? So, lo and behold, oh, my graph wasn't too off here. I'm right in the right neighborhood, around, actually exactly at that point, at 0 comma negative 4, it's where this curvature happens. But at this point, the line continues down like that, so it doesn't curve back up again. And it shouldn't, actually. Okay? So, because, I will correct this curve before I post these notes on Canvas, because there is no other x-intercept or zeros, so this line will continue in this direction. So this would have been the right thing, because these are all the x-intercepts we have. We do not have any other x-intercepts, right? So this line goes right through, and it does not curve that way at all. Okay, so here, and then let's snap to those intercepts. So we had intercepts at, what we calculated was at 1 comma 0. Oops. 1 comma 0 right there. So let's label it. We also calculated another 0 or x-intercept as 4 comma 0 right there. Let's label it. And then we also had the y-intercept at 0 comma minus 4. Oops, that's comma. And let's label that. Again, because we have only 2 x-intercepts, we know that from the equation of the polynomial, then the line here does not curve back. So we can predict. We could predict that this line goes right through and continues in that direction, and it does not curve back up towards the x-axis, because it's not going to cross the x-axis again. Okay? All right, so let's switch back to the dot camera. So here we have, here we have another polynomial. Let's find the x-intercepts, i.e. these are the zeros of the polynomial. Which is the same thing as saying y equals 0, right? That's where the x-intercepts are. So we have the factors given to us. That significantly makes this a lot easier, significantly simplifies the calculation. So x minus 1 equals 0. If that factor is equal to 0, then the whole thing is equal to 0, right? 0 multiplied by anything is 0. So that's the 0 of the polynomial, and it has multiplicity. Look at the power. Multiplicity 2, right? Equal to 2. So here we have the x-intercept as 1 at 1 comma 0. The second factor, x plus 4 equals to 0. Then we have x equals minus 4. And that has multiplicity. Look at the power, multiplicity 3, right? We care about if these multiplicities are even or odd. That's what we care about. Okay, so even, odd, and this is minus 4 comma 0. Okay, so the y-intercept or this is when x equals 0, right? Let's replace x with 0 and find the value of y. right? So this is minus 1 squared is positive 1. 4 cubed is positive 64. So y equals 64, which means this will be, the y-intercept would be at 0, 64. Okay? All right, so let's plot. Let me move this up as much as I can. Okay, at some point I have to move this page up, otherwise you won't see the graph. But let's plot what we can. So 1, 0. So let me increment this as 1. So 1, 2, 3, and then negative 1, negative 2, negative 3, negative 4. Right? And this is way down, way off the page here. So I'm not going to be able, that's why we're going to go to the computer and see the best graph we can draw. But for now, for the manual calculation, the x-intercepts are going to be at 1, 0, right there, at the bottom of your screen, and negative 4, 0, right there. Okay, so let me move this page up. 0, 64. That y-intercept is going to be way up, way up, way up here somewhere. It's definitely going to be off the page. So let's look back at these multiplicities. At 1, 0, that's that point, we have multiplicity 2, which is even. So whichever side the line of the graph will come, it will not cross the x-axis. It will stay on the same side. It will bounce to the same side because multiplicity is even at 1, 0. But this one, at minus 1, minus 4, 0, the graph will be going through the x-axis because the multiplicity is odd. So at this point, the graph will hit it, whether it's coming from this side or that side. It'll hit it and it'll cross it. Okay? So, but from which side? From which side the line is coming from? We have to have an idea about that. So let me test. Let me pick a test point on the left of negative 4, 0. Because we need to find out whether the y value is positive or negative. Because if the line, at this point, I don't know because I'm drawing this manually, right? So we don't know. I want to keep everything on the screen here. So I know what's going to happen to the graph of the polynomial once it hits this point. It's going to cross the x-axis. But what I don't know is whether the line is coming from above here or whether the line is coming from below. From which side, I don't know as of now. So I have to pick a test point. The test point would be some easy x value to the left of x equals negative 4. So let me pick x equals negative 5. Any point to the left of this would do. So what's the reason for that? So I'm going to pick x equals negative 5, and I'm going to evaluate this function at x equals negative 5. If the function is negative, then I know the line is coming from below this point because that's where the y values are negative. But if I pick x equals negative 5 and evaluate the function at that point, and if I get a positive value for the function, then I know the line is coming from above, where the y values are positive and crosses the point at that point to the other side. And then it's going to go towards that and then come back. Okay? So well, we may not need the test point. So we have the y-intercept, right? We have the y-intercept, so we're not going to need the test point. But the test point, we could use it, and it would tell us, it would definitely tell us that if I included a -5 there, for sure it would turn out to be negative, the result of the function, which means the line would come up from the below the x-axis, go all the way to that point 0, 64, hit it, curve back down, hit this point, not go through this point, but bounce back to the same side because multiplicity is even here. Okay, once again, before I draw the graph, for 1, 0, for this point, the multiplicity is even. So when the line hits it, the line of the graph hits it, it's not going to go through. It's going to bounce back to the same side. But the multiplicity for this 0, -4, 0, is odd. So the line of the graph is going to hit this point and cross the x-axis. So let's do that. So we have the y-intercept of here, and we know the line is going to go through this. So it cannot come from this side. It has to come from this side. Like that. And on this side, it's going to come and hit this point, and it's going to bounce back to the same side and go like that. This is as best as I can. This line, let me put this point up here, because this point cannot go, this line cannot go above the line, the point as I had drawn it. So let me make this line better. So this is going to come down like that, go through this -4, 0, and then it's going to come down and hit this point, touch it. Multiplicity is even at this point, so it's not going to cross the x-axis. It's going to curve back up and go up like that. So this is a better graph. Okay, so that's manually. Let's go back to the computer. So we have the graph of p of x equals x minus 1 squared times x plus 4 cubed. Okay, like that. So let me zoom out. So you can see the computer's graph is very, very detailed, and you can see what happens at that -4, 0 right there. At that point, something interesting happens, and also at 1, 0 right there, right? And if I zoom out, you can see that the y-intercept is at 0, 64, right? Let me snap to it. So 0, 64, right there, where you have the y-intercept. There is only one y-intercept, but I've zoomed out so much that the lines are so close to each other, you think that there are multiple y-intercepts. No, there is only one y-intercept, which is at that point. We can zoom to it. We can investigate all of these points one by zooming into them, but we cannot look at them all at once. So that's where the line 0, that's where the graph of this polynomial goes through the y-axis, 0, 64. Notice that where we had the even multiplicity at 1, 0, the line bounced back to the same side, right? We knew that because multiplicity for 1, 0 was 2, which is even, and so that we would expect the line to bounce back to the same side from which it's coming from. So that's what happened. -4, 0 had odd multiplicity. So let's zoom in onto these. It had all multiplicities, so, and of course you can see it go through it in a rather nice cubic function pattern. And that is, yeah, when you look at the polynomial, let me expand this. So look at the power, look on the left here, look at the power of x plus 4 term. It's cubic, right? So that's why you have this kind of pattern, a cubic function pattern at that juncture, at that 0 of the polynomial, at that x-intercept. You have a nice cubic function pattern there. So that's why, as I said earlier, we study all these fundamental graphs like quadratic function, cubic function, absolute value function, because you can analyze more complex curves like the curves of these polynomials in terms of their cubic behavior at certain junctures. So you can segment a more complicated graph like this into segments that are cubic in form, or into forms that, like this one on the right, this one, that is quadratic in form. Okay, that's what I was referring earlier, that this is why we study quadratic functions, cubic functions, square root functions, absolute value functions, because you can analyze these more complex graphs in terms of those more fundamental graphs. Okay, so thank you for persisting through this. I know this video is long, but it had to be. In order to make everything clear, I had to make this video this long. So I'm thankful to you for persisting through it and spending the time. So for now, have a nice day, and I'll see you all next time.